In this section, we'll learn about a very interesting plotting technique called quantile-quantile plot, often in short referred to as QQ plot. So let's take a problem that QQ plot helps us solve. Imagine if I have a random variable x, right? Okay, and let's say I have 500 observations, x1, x2, x3, so on and so forth. Let's say x500. These all are observations from the random variable x. Okay, so these are all samples or observations from random variable x. Now I want to determine if, so the question that I have is x Gaussian distributed? Is x Gaussian distributed? Okay. Now to answer this question, there are multiple techniques. One of the simple techniques is QQ plot, which is a plotting technique, right? There are other techniques in statistical testing. Okay, we have tests like K-S test, Anderson-Darling test, etc. By the way, we'll learn about statistical testing later in this chapter in the section hypothesis testing. Okay, we'll learn K-S test in this course, which is one of the more generic tests. Okay, but QQ plot is one of the simple graphical methods. QQ plot is a plot or a graphical method to determine if a random variable is Gaussian distributed or not. It gives some very, very interesting perspective. Okay, of course, the tests are far more powerful. Like Anderson-Darling is probably one of the very interesting and probably one of the strongest tests to determine whether a random variable is Gaussian or not. But today, in this section, we will look at QQ plot. Okay, what is QQ plot? Okay, so we'll see how to plot QQ plot first, how to plot, and then how to read a QQ plot, right? So let's go step by step. The first step is you have your x1, x2, x500. You sort your xi's. You sort your xi's and compute their percentiles. And compute percentiles. Okay, that's the first step in plotting your QQ plot. Okay, so when you sort xi's, okay, suppose you have x1, x2, so on and so forth, x500, right? You can sort them. You can sort them and get, let's say, x1 dash, x2 dash, so on and so forth, x500 dash, such that x1 dash is less than equal to x2 dash, so on and so forth. Okay, so this is ascending, sorting in ascending order. Okay, such that this is the smallest, such that this is the smallest, and this is the largest. Once you sort them, you can compute percentiles, right? Once you sort them, you can compute percentiles. Since there are 500 values here, the first percentile value will be at x5 dash, right? So your x5 dash is your first percentile. Your x10 dash is your second percentile. This is your first percentile. This is your second percentile. Your x15 dash is your third percentile because you have 500 points here, right? So on and so forth. Your x500 dash is your 100th percentile. Okay, so let me represent each of these percentile values as follows. The first percentile of xi's, I will write it as x1. The second percentile, I'll write it as x2. See here, I'm putting this in the superscript, not in the subscript, and I'm putting it in brackets. So this says first percentile. The first percentile value of xi's. This is the second percentile, this is the third percentile, so on and so forth, the 100th percentile of xi's. Okay. This is just notation here. I'll reuse this notation as we go forward. So the first step is sort xi's and compute percentiles like this. Okay, so this is very simple. We know how to compute percentiles from our exploratory data analysis chapter. So all this is very straightforward for us. The second step for us is, okay, now let's create a random variable y, which is n01, Gaussian distributed with mean 0 and variance 1, and standard deviation also equal to 1. So from this distribution, let me create y1, y2, y3, so on so forth, let's say y1000. So these are 1000 random variables. These are 1000 observations from a Gaussian distribution, from a standard Gaussian distribution. This is nothing but your standard Gaussian distribution, right? Your standard normal distribution or standard Gaussian distribution. Okay, even these values you can sort them, and you can have y1 dash, y2 dash, y3 dash, so on and so forth, y1000 dash in ascending order. And on top of them, for this, now I can compute percentiles. Okay, where y1 is the first percentile, y2 is the second percentile, y3 is the third percentile, y4 is the fourth percentile, y100. Right? I can compute this, right? Now to determine, so remember here in the second step, I'm taking a random variable y which is n01. Okay, so this is my second step. In the first step, I computed the percentiles of my random variable x, which we want to determine is Gaussian or not. In the second step, we took a standard normal distribution and we computed its percentiles. Okay, third step is where we plot. Okay, so third step is plot QQ plot. So plot QQ plot using my x1, x2, so on and so forth, x100. I also have y1, y2, so on and so forth, y100. Right? I have these two percentile values. Now I'll use these percentile values to plot a QQ plot. Let's see how to plot a QQ plot. Okay. So let's assume on this axis I'm plotting my n01 random variable, which is y. Okay. These are often called as theoretical quantiles. Okay. And on the y-axis here, I have my x, random variable x. Okay. So any point here, so the way I plot, okay, so these are all the values of x's. Okay, this is values of x, this is values of y. Now any point here, so I'll plot 100 points here as follows. I'll plot, take a point, okay, I'll plot, let's say the x-axis for this, the x-axis for this will be y, let's say this is y5, okay. Then the corresponding y-axis for this point will be x5. So this point is nothing but y5 comma x5. Similarly, I'll plot 100 points such that my x-axis is y1, my y-axis is, again, I've swapped these two random variables, but that's okay. Okay, similarly, y2 and x2, y3 and x3. I get 100 such pairs. I'll plot all of those points in this plot. Okay. Now, when I plot points like this, let's say I'll show you actually an output so that you'll understand it better. Okay. So let me go here. Okay. This is a QQ plot, by the way. This is a QQ plot where on the x-axis I have n01. Okay, which are your random variable y. On the y-axis here, I have random variable x values. Okay, of course, these are ordered values. Okay, ordered and percentile values. Now, every point here, this point here corresponds to the 99th percentile. Okay, this point corresponds to the 99th percentile. Okay, so its x-axis corresponds to the 99th percentile of y. So this point itself will have its x-axis here as y99 and its y-axis here as x99. Okay, so I get exactly 100 points here. Each of my points correspond to the x-ith percentile and the y-ith percentile for all I going from 1 to 100. Okay, this is how I'm plotting my QQ plot. Now this is where things get very interesting. If all these points, if all of your points roughly lie on a straight line, if this is the best part actually, if your yi xi points lie for all, of course, for I going from 1 to 100, if they lie on a straight line, then your random variables x and y have similar distribution. So the way we took our y to be n01, right? So if this lies on a straight line, you can say that x also has a Gaussian distribution. X also has a Gaussian distribution. Of course, it need not have mean 0 and variance 1. Actually, you can compute the mean and variance from this plot itself. What is the mean of n01? The mean of n01 is 0. Okay. The corresponding value we can take here. Okay. This is roughly the mean of your x, roughly, not necessarily, because these points are drawn using percentiles, right? And not simple the mean computation, right? So if all these points, the 100 points that we computed here, if they lie on a straight line, then your random variables x, which is on y-axis here, and your random variable y have a similar distribution. Okay, if y is Gaussian, this is also Gaussian. If this is if this is uniform distribution, this will be uniform distribution. If this is Pareto, this will be Pareto, etc. Okay, so this is very important to understand. Oftentimes, QQ plots are often used to understand whether a random variable is Gaussian distributed or not. Okay, this is the question mark. It also has other applications that we will cover at the end of this section. Okay, so let's go and go through some simple code here. Okay, so that it's easy for us to understand. So the code here is very straightforward. Okay, I'm just importing NumPy, PyLab, and SciPy statistics. And here, this is how you generate a sample of random numbers. Okay, this is how you generate observations from normal distribution. Okay, so NumPy has a package called random, which has normal. Now this location is nothing but mean. Okay, this is nothing but standard deviation. Okay, location and scale. The size equals to 1000 says. So what this says is generate random numbers or sample randomly from a Gaussian distribution, from a normal distribution with mean 0 and standard deviation 1, and generate 1000 such samples. Okay, and put all of the 1000 values in this variable called std_normal, standard normal. Okay, this is how you generate random observations from Gaussian distribution. Okay, from Gaussian distribution. Very simple way, and NumPy just lets you do it in a single line of code. Okay, now you can get percentiles. Of course, you can easily get percentiles. So all that I'm doing here is I wanted to print percentiles. I'm just running a loop between 0 to 100, right? I'm just saying print I comma. I can compute the percentile. So I can give it standard normal. I've just input the standard normal here, which has 1000 values. And I'm saying get me the 0th percentile, first percentile, second percentile, third percentile, etc. That's what it's exactly doing, right? That's what it's literally doing. Okay. Now having said that, now let's do something interesting. Okay. So that's how you generate random numbers from a normal distribution. Okay. Now let's take it to the next level. Okay. Imagine if I have a variable measurements, in which I'm generating random normal values or Gaussian values with mean 20. My mean here is 20 and my standard deviation here is 5. And imagine if I'm creating 100 such samples. Okay, so measurements are 100 samples from n 20, 5. Okay, and they're 100 samples. Now, how do you get QQ plot? I told you the 3 steps, right? We gave the 3 steps, but it's much easy. In the statistics module of NumPy, there is something called a probability plot. Okay, here I can say that I want a QQ plot or a probability plot between my variable, which is measurements, and I want to compare it with normal. So dist equals to normal says I want to compare it with standard normal variate. It says compare it with n01. Okay, and for plotting, use this library called PyLab, and I'm just saying pylab.show. Simple, very simple here. Now that generates this plot for me. Just these 2 lines of code. So what is my x-axis here? My x-axis is n01, right? What about my y-axis here? My y-axis, because I generated my measurements from mean 20 and variance 5, right? So these are coming from n 20, 5. Since both of them are coming from Gaussian family of distributions, of course, their means and variances and means and standard deviations are different. But since both my random variable y here and my random variable x here have same type of distribution, both of them x and y are Gaussian. Because x and y are Gaussian, okay, I get all of these points mostly lying on a line. Now you might ask, this point doesn't lie on a line. This point is slightly away from a line, and there are some points here which are away. So like these points are away from the line. There is this point which is away from the line, right? So this we try to just plot this red line here tries to be the best line that will go through most of the points. Okay, you might argue that these points are not there. Okay, now let's do a simple hack. Instead of taking 100 observations here, I would argue that this is just because of the sample size being very small. Instead of 100 samples here, I'll just change this to 1000, and let's just run it now. Sorry, something went wrong. Oh, sorry. This is the plot. Location size equals to 1000. NumPy plot. Okay, it's generating an error. Let's see what the error looks like. Okay, if I have 100 here, does it work? Okay, there is an error here, but let me fix it for you. So NP is not defined. Okay, why is it so? I'm importing NumPy as NP. Okay, let me just run it from the start. Okay, now NP is defined. Yes. Okay, I think I just didn't run it. So it's very easy to read the errors here, right? It says NP not defined. I just fixed it. So instead of 100 now, if I make this 1000, let's see what happens. If I make this 1000 here, okay, this is the same code. The moment I made it from 100 to 1000, okay, I just made it from 100 to 1000. More of the points fall on this line, except for the extreme ones, right? Even if you look at the difference between 100 and 1000, right? On 1000, more and more points are lying on the on the straight line, right? So it could just be because of this discrepancy. So let's assume I put it as, let's say I just make it, let's say 50. Let's see what happens. Okay, when I make it 50, right, there is more deviation from the straight line when I make it 50, right? This is a probability plot. This is a probability plot between a normal distribution and normal distribution, of course. Okay, now if I make it 50,000, let's see what happens. Now the moment I made it 50,000, like as my sample size increases, as my number of samples increases, okay, more and more points start lying on this, more and more points are closer and closer to this line. Okay, so it's not the problem with the plot itself. So whenever you have a sample size which is small, QQ plot will not work. That is a major limitation of QQ plot. So if number of samples, if number of observations, if number of samples or observations is small, okay, it's hard to read, it's hard to interpret QQ plot. Okay, this is a major limitation, right? I'll show you a counter example here. Okay, let's just go down a little. Suppose this is where things will get very interesting for us. So now instead of generating from, so here if you recall, in this case I generated data from a normal distribution, right? Now I'll change it and generate it from a different distribution called uniform distribution. We'll learn about uniform distribution in the next section. Okay, this is a different type of distribution, okay, which has something called low and high, and I'm generating 100 samples from here. And now what I'm doing here is on my x-axis, I have a Gaussian distribution. Sorry. On my x-axis, I have a Gaussian distribution. On my y-axis, I have a uniform distribution. Of course, these points should not lie on a line, and they don't. See, there are more and more points which are going farther and farther away from the straight line, right? So what this means is in the extremities of my distribution, points are diverging more and more. That's what it means. Now this will become much more clear. Instead of taking 100 points here, if I take 1000 points here, okay, let's take 10,000 points here. Okay, if I run this code now, wow, there is significantly more deviation now. This is, again, this is uniform, and this is Gaussian. So more and more points are deviating from the straight line. So if most of your points, or if all of your points lie on the straight line, then you can conclude that the distribution that you have on your x-axis and the distribution that you have on your y-axis are from the same family. Okay. Having said this, there is another very interesting application of QQ-plot. Okay. So we saw QQ-plot as a method to answer this question, right? Is X normally distributed? Is it so? This is a question we try to answer here. But there is another related question, which is, if you have random variables X and Y, are X and Y, okay, are X and Y not are, so I should actually write it as, does X and Y have the same distribution or similar distribution, right? Instead of, so because in all of my plots here, okay, instead of taking Y as N01, I could have taken Y as anything. Here I've generated 1000 variables, right? It did not be from the Gaussian distribution. It could be from any distribution. Okay, so given any two random variables, so let's assume X and Y are two random variables, using QQ-plot, exactly following the process that we did, we can determine whether X and Y have similar or same distribution or not. Okay, so QQ-plot is a graphical technique, just to quickly recap, to answer these two types of questions. Is X coming from normal distribution, and are X and Y coming from same distribution or similar distributions? These are the two interesting questions that QQ-plots help us answer.